Okay, welcome to another Python video with me, Rich Cooper. This video is to go with my other YouTube video that I've just uploaded about Huffman compression and decompression. I advise you watch that video first, where I explain how the algorithm works before looking at this one. So we're going to run the program to see how it works, and we will see that if I type in the same string as I did with my other video, she sells seashells, it goes away and it generates a Huffman tree and it creates some binary codes. These are different to the ones in my other one, but if you the key information is that the original file size was 140 bits and the compressed file size is 49 bits, and that's what I predicted in my other video, which is actually a compression ratio of 2.9 to 1. And there is my compressed message. Okay, so what are the problems that you're going to need to solve if you're going to code this yourself? I'm not going to explain how my code works. I think it's just better if I explain how you should go about solving the actual problem. So the first thing that you need to do, real easy problem to solve, is you need to input some data to compress. So that's just a string input, and you can then calculate how many bits that is. Should be multiplied by 7 because it's ASCII, which only needs 7 bits, not 8, because it's not the extended character set. And then we just need to extract some key information from that, and the key information that we need is to grab the frequency of each letter. So what we want to do is essentially create a table that says this letter occurs X number of times in the string, which is what this bit of code here does. What we then need to do is we need to combine the nodes. Now, if you watch the other video, you can kind of see how that works. When I'm doing it on the whiteboard, you can see that we have to kind of combine nodes together and create a tree, which then we can assign binary pathways to. And in effect, that's what this recursive function does. It orders the nodes in order of size, and then it combines them together in a series of binary pathways, and it allocates a string of 0 or 1, depending whether it's the left-hand item or the right-hand item. And it continues to do that until there is only one node left, and that's effectively what this is. Now, this isn't quite accurate in terms of the one that I drew on the whiteboard, and the reason is that there's some duplication goes on. So we see, for example, that we see like 6S appears here, and it also appears here. All right, it's just the way that the program's outputting the information. It doesn't quite accurately draw it, but what it does do is it produces our unique set of binary codes for each letter. And just as it did on the whiteboard, the more frequently occurring letters in the string are the ones that require the fewest bits to encode, and the least frequent ones are the ones that require the most number of bits to encode. And that's typical of what the Huffman compression does. So once we've done that, we just need to write a piece of code that looks at the tree, the Huffman tree, and then says, okay, what's the best way of explaining this? It does this. It says, right, okay, where's the letter S? So the letter S is over here. Is the letter S by itself? No, so it means we're going to have to go at least one level down. But while we're here, we're going to grab this binary digit, because we know that that's the binary digit that we need. Then we go down to the next level and we say, right, is S here? So we know it's not there, but it is here. So we grab the second binary digit, which creates our code of 1, 1, which you see here. Now the program knows it needs to stop because there's only one letter left, and so it knows that there's not a level below, so it doesn't need to check for another letter and another code, so it stops. Then it looks for the next letter in the string, which in this case would be H, so we go to H. Program looks and says, right, we grab that 1. Then we go to the next level down and we see that we've got AH, so we grab the 0, and then we keep going until we find H by itself, which is down here. And you can see that in order to actually get to that code, it needs to go 100 1011. Okay, so this is effectively how the program does it. And oops, and this bit of code is essentially what checks to see what the codes are. Then it's a pretty simple matter once you've created that table of letters and binary digits to just go through your string and then create your code. So that's just that simple bit of code there. It just concatenates into a great big binary digit, as you can see here, and that's compressed data, and we just convert that to a binary number here. So I'm just going to scroll through this slowly. You guys, if you want to get this code, then just type it in, and learn something about coding while you do it. And if you make mistakes, then figure out why you've made mistakes. If you're just going to use my code, I know a few people have emailed me and said, please send me the code. And I think, well, have a crack at it first, because if you don't try it yourself, you're never going to learn anything if you're just going to copy someone else's code. And I'm sure this can be improved on if you're a computer programmer. You can probably, look at this and rip it to shreds. But I think the best way to learn to code is to give yourself a problem and then try and solve it. Just by, if you know the algorithm, you should be able to write some code for it. And there's a little bit of code at the end that just figures out what from the code, it sort of uncompresses it. That's this little bit here. So all it needs to know is it needs to know what the binary compressed code is, and it needs to know what basically needs to know what this is, and it needs to know what this is, and then it can easily decode. Now here's some stuff that still needs to be done with this program. So if you want to give yourself a little challenge, I suggest trying, and please comment on my video and suggest how it could be improved, or suggest what could be done to make it a more efficient program. I'd love to hear from you, because I'm a student just like you. So anyway, hope you've enjoyed this video. Hope you found it useful. Remember to watch my other video on Huffman compression, decompression, and if you found it interesting, useful, or just not boring, then please like, subscribe, share, and leave a comment. Thanks very much for watching.